Hello and welcome to another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 10, Lesson 2 on factoring polynomials. Factoring is a skill that you've learned for many years now, both in Algebra 1 and earlier in this course in Algebra 2. And we've seen many different types of factoring, right? Difference of perfect squares, greatest common factor, factoring trinomials, and factoring by grouping. Today, we're going to just add one additional type of factoring to that list, but more importantly, we're going to see how factoring can reveal important things about the structure of our polynomials. So let's jump right into it. Here we go, factoring by grouping. Just as many whole numbers can be factored, so can many polynomials. We factored quadratic polynomials extensively in Unit 7. Factoring higher degree polynomials becomes increasingly more challenging and increasingly rare in applied problems. We will look at limited factoring of cubic and quartic polynomials. So cubic polynomials, those with a degree of 3, and quartic polynomials, those with a degree of 4. So let's jump into it in Exercise 1 and review how to factor by grouping. Exercise 1. Recall that some cubic polynomials can be factored by the use of grouping. For each of the following cubic polynomials, factor them completely, and then identify the zeros of the polynomial. Awesome. Well, I know that we've done factoring by grouping a few different times in this course, but let's go through letter A together. Here we have x cubed minus 5x squared minus 9x plus 45. Classic cubic polynomial written in standard form, decreasing degrees of the terms, right? Decreasing exponents. So let's take a look at how we factor this by grouping. Here we go. So remember, by grouping, as long as we've written this thing in standard order, what we're going to be doing is we'll group the first two terms together and the second two terms together. Now what we're going to do is in the first two terms, we're going to factor out a greatest common factor. In this case, that's x squared, which will leave us with x minus 5. Now, if factoring by grouping works here, and it sometimes does and sometimes doesn't with cubics, then whatever we factor out of the second two terms needs to leave us with an x minus 5 inside of parentheses. To do that, we're going to have to factor out a negative 9 from that negative 9x plus 45, and that will leave us with what we want, which is that x minus 5 term. X minus 5, or x minus 5 factor, that x minus 5 factor can now be factored out of that more complex expression to give us x minus 5 times x squared minus 9. Sometimes this is where we end up stopping, but we can now factor our x squared minus 9 as x minus 3 times x plus 3 by the use of the difference of perfect squares. And now we've factored completely. And I know we've factored completely because all of these are linear binomials, right? X to the first, and none of them have a greatest common factor. Now the problem also asked us to identify the zeros of a polynomial. Now the zeros of a polynomial are very important. We've talked about them repeatedly. They are the values of x that will create the polynomial having a value of 0, or will result in the polynomial having a value of 0. The zero product law allows us to say that any value of x that will make any one of these factors equal to 0 will make the polynomial itself equal to 0. So obviously we've got 3 of those things. You could probably figure that out without writing this down, but if x minus 5 is 0, then x would be equal to 5. If x minus 3 is equal to 0, then x would be equal to 3. And if x plus 3 is equal to 0, then x would be equal to negative 3. We love it when our zeros are whole numbers like that. They aren't always, as we'll see in letter B though. So what I'd like you to do now is pause the video and see if you can factor this cubic polynomial by grouping and solve for its zeros as well. Pause the video now and see what you can do. All right, just like before, what we're going to do is we're going to group those first two terms together and those second two terms together, and I'll put a plus between them. In the first two terms, I can factor out a 4x squared. That'll leave me with 3x minus 4. And in the second one, notice that's negative 3x plus 4. So if I factor out a negative 1, that's going to leave me with that 3x minus 4. Okay, now I can factor a 3x minus 4 out of both of those two larger terms. That will leave me with a 4x squared minus 1. And just like before, and this is the most common thing that you'll see happening with factoring by grouping, I can then factor this as the difference of perfect squares. So, to begin with, this is my complete factoring of that polynomial. Now, if they say completely factor a polynomial and nothing else, then I'm done at this point. The problem does then state to find the zeros of the polynomial. At this point, this is a little bit trickier, and I worry sometimes because some students will literally say, oh, to figure out the zeros, I just look at the numbers that are attached to x and I do the opposite. So -5, +5, -3, +3, +3, -3. And then I'll get some students that'll look at something like this and go, oh, we've got a zero of 4, 1, and -1. Totally not correct, right? The way I'm thinking about this is what value of x will make 3x minus 4 equal to 0? What value of x will make 2x minus 1 equal to 0? And what value of x will make 2x plus 1 equal to 0? Now, if you can solve those in your head, fantastic. If you can't, obviously what you want to do is you just want to take a little bit of time to write down this two-step equation, hopefully without all the red, right? Add 4 to both sides, more red, and divide by 3. And I have plenty of students over the years who are able to look at something like 3x minus 4 and immediately say, well, its 0 would be 4/3. Likewise, 2x minus 1 equal to 0. That would be 2x equals 1 and x equals 1/2, skipping a few algebraic steps there. And 2x plus 1 is equal to 0. 2x is equal to -1, and x is equal to -1/2. And again, I want to reiterate, the only reason I'm doing that is because it told me to find the zeros of the polynomial based on completely factoring it, okay? And we've got all of these fractional zeros. That's fine. Nobody says that the zeros have to be integers as they are in letter A. Let's keep going. Exercise number 2. Like quadratic polynomials, higher degree polynomials can have real roots and imaginary roots. Solve the polynomial equation below for all its solutions, both real and imaginary. All right, well, I'd like you to take a shot at this yourself. We just got done with our unit that covered imaginary numbers and quadratics that had imaginary solutions. So see what you can do, factor this completely as much as you can, right? And then see if you can find the zeros, and there will be some of them that are imaginary. Cool, let's do it. So just like we did before, I'm going to group these two and these two. In our first set of parentheses, what I can do is factor out an x squared, and that'll leave me with an x minus 4. And in the second set, I can factor out a 9, and that will also leave me with an x minus 4. I can factor the x minus 4 out of that larger expression and be left with x squared plus 9. Now I'd like to pause just for a second because a lot of students, you know, they will just look at something like this and they'll go, x squared plus 9, maybe x minus 3, x plus 3. This is not the difference of perfect squares, right? As well, you know, I might get some people that'll say, well, x plus 3 times x plus 3, but x plus 3 times x plus 3 is x squared plus 6x plus 9. In fact, if you think about it, right, if I was trying to factor this by, let's say, using a trinomial, right, it would be x squared plus 0x plus 9, right? I'd be looking for two numbers that had a sum of 0 and a product equal to 9, but there are no two numbers that have a sum of 0, not real numbers, that have a sum of 0 and a product of positive 9, right? 3 times 3, well, that's going to be 9, but its sum would be 6. -3 times -3, that would be a product of 9, but a sum of -6. 1 and 9 don't work. -1 and -9 don't work. So this cannot be factored using real numbers. That's okay. I don't need it to. This thing didn't ask me to factor completely. It just asked me to find the zeros, right? Or the real roots. In that case, what I'm going to do is I'm going to take x minus 4 and set it equal to 0, and that'll give me x is equal to 4. Awesome. And then I'll take x squared plus 9 and set it equal to 0. That will give me x squared equals -9. I'll take the square root of both sides. Remember, it's an even-powered root, so that's going to give me plus or minus the square root of -9. And that will be x equals plus or minus 3i. So there are, in fact, 3 zeros to that equation, 3 solutions to that equation. Only one of them is a real number. The other 2 are imaginary. Okay, let's keep going. See, prior to our work with imaginary numbers, we would have had to say that the only solution to that equation was x equals 4. But now we can say both x equals 4 and x equals plus or minus 3i. Recognizing structure to factor. Sometimes we can take advantage of structure that we recognize from earlier factoring, all right? And I'm talking about factoring by the difference of perfect squares, factoring trinomials, things like that. So let's take a look at exercise number 3, where we try to identify sort of more complex structure, but use sort of earlier factoring techniques to deal with it. Exercise number 3. Factor each of the following polynomials completely over the set of integers. We'll talk about what that means a little bit later, that over the set of integers. But let's take a look at exercise A right now. Here we have x to the 4th minus 16. Now clearly, x to the 4th minus 16 is not an example of a trinomial. There is no greatest common factor. But we can think of x to the 4th, and let me write this a bit bigger, minus 16 as x squared squared minus 4 squared. So we can really think about this as the difference of perfect squares. And in fact, x to the 4th minus 16 will factor into x squared minus 4, times x squared plus 4. X squared minus 4, that is again the difference of perfect squares, so it can be factored as x minus 2 times x plus 2. But then I'm going to have to leave x squared plus 4. If all I can use are integers, then I cannot factor x squared plus 4, just as I couldn't factor x squared plus 9 in the last example, right, or in the last exercise. So this is it. I'm done. But I had to recognize, right, that x to the 4th minus 16 could be factored as the difference of perfect squares, x squared minus 4 times x squared plus 4. Let's take a look at letter B. Here we have y to the 4th minus 10y squared plus 9. Now this is essentially the same structure. I'm going to just write something else down. This is really the same structure as this, n squared minus 10n plus 9, right? I claim it's the same structure because it's trinomial, and this term is just this term squared, right? So it's absolutely the same structure, it's a trinomial. The difference is, right, we really have y squared squared and y squared to the 1st. So if you can factor this, you should be able to factor this. And let's talk about what n squared minus 10n plus 9 would be. Right? Factoring that trinomial, we would just have something like this, n minus 1 times n minus 9, right? Negative 1 times negative 9 gives me positive 9, and negative 1 plus negative 9 gives me negative 10. But since I'm dealing with this and not this, what I really have is y squared minus 1 times y squared minus 9. Right? So I recognize the fact that this trinomial really has exactly the same structure as this one, which allows me to then factor it using standard trinomial sum product considerations. Now, both y squared minus 1 and y squared minus 9 are the difference of perfect squares. So I can further factor them, and I've got this now beautiful factorization, y minus 1 times y plus 1 times y minus 3 times y plus 3. 4 beautiful factors. All right, awesome. Let's go back up and take a look at that last one. N to the 6th minus 4n squared minus 81n squared plus 324. All right, look, if they're asking you to factor something and it's got 4 terms to it, then very, very likely that factorization will be using factoring by grouping. Whether it's a cubic or not, doesn't matter. And this is definitely not a cubic, it's an n to the 6th, all right? So I'd like you to pause the video right now and just use our standard factoring by grouping to see what you can do in letter C. All right, let's do it. So 4 terms, I'm going to always consider factoring by grouping if I'm asked to factor. So we've got those first 2 terms and the last 2 terms. The first 2 terms, I can factor out an n to the 4th, which will leave me with an n squared minus 4. Now I really want an n squared minus 4 to pop out in the other one. And I have to hope that somehow 81 and 324 are related. Now if I'm not sure, then I'm going to pull my calculator out. I'm going to take 324, I'm going to divide it by 81 to see, hey look, actually 4 times 81 is 324, right? So come back in, if I factor out an 81, I'm going to yet again have that n squared minus 4. Right? I can't factor out any n's because the 324 doesn't have any, but now I can write this as n squared minus 4 times n to the 4th minus 81. All right, but there's more I can do. The n squared, I'm not going to have any room, but there's definitely more I can do. So I'm gonna see if I can bring all of this down here to give myself some more space. Right? N squared minus 4 I can now make into n minus 2 times n plus 2. N to the 4th minus 81 I can make into n squared minus 9 times n squared plus 9. And I'm almost done, except n squared minus 9 is also the difference of perfect squares. It can be factored as n plus 3 times n minus 3. And the n squared plus 9 I can't do anything with. Wow. Look at that factorization. Isn't that beautiful, right? And think about how many times I factored there, right? Initially, I used factoring by grouping just to get to here. I then used the difference of perfect squares to take this thing and factor it as n minus 2 times n plus 2, and the difference of perfect squares to make this one into n squared minus 9 times n squared plus 9. There's nothing I can do with the sum of perfect squares, not if I'm factoring over the set of integers. And again, I'll explain that piece of terminology in just a moment. But I can definitely factor this one, and then I have to leave n squared plus 9 as is. All right, well, let's talk about what I mean by that factoring over the set of integers thing. Why over the set of integers? We have almost always factored only in terms of integers, because that is what is mostly done when numbers are factored. Right? We don't tend to factor the number 2/3. We don't tend to do that, right? We don't tend to factor the number 6.75. What we tend to do is factor numbers like 12 or 36 or 50, right? But we can break into products using non-integers as well if we're sort of given permission. So looking at 3 different things, right? X squared minus 9, x squared minus 2, and x squared plus 4. Now, if you're wondering where this is on the worksheet, it's not there, right? This is a little Kirk aside moment, if you will. Right, x squared minus 9, we can factor that into x minus 3 times x plus 3. Those are factored under the integers, right? Difference of perfect squares. But if you looked at x squared minus 2, you'd say, well, sure, x squared's good, and the minus is good, but the 2, well, the 2 isn't a perfect square. And yet, we could still factor that, right, as x minus the square root of 2 times x plus the square root of 2, right? We've broken it up into a product. Now that would be factored under the reals instead of the integers because the square root of 2 is not an integer. It's not even a rational number. Now x squared plus 4, that thing, right, is like, well, geez, that's not even a difference. Not even a difference. And yet, you can factor it into x minus 2i times x plus 2i. And that would be factored under the imaginaries, all right? So in other words, we could break that up into a product as long as we brought imaginary numbers in. Now, whenever you're just told to factor something, all right, and they don't say under the reals, the imaginaries, or whatever, then the baseline assumption is you're only factoring under the integers. All right, so you're never going to bring in like square roots, you're never going to bring in i's or anything like that. But I do want to point out that with some flexibility in your thinking, you can actually factor both of these things using, believe it or not, the difference of perfect squares. And you might say, well, how is that the difference of perfect squares? Well, you really could think of x squared plus 4 as being x squared plus negative 4. And negative 4, right, is 2i times 2i, right? 2i times 2i is negative 4. So, whoops, I don't want plus there, I want minus. So I could think about that as the difference of perfect squares again, as long as I consider negative of 4 a perfect square by using imaginary numbers. Okay, anyway, just a little aside there to explain that piece of terminology. Now what we're going to do is we're going to look at the last type of factoring, and this is definitely the most complex of all types of factoring because it relies on two formulas that we looked at very recently. There are two new factoring patterns that you're expected to learn in Algebra 2, known as the sum and difference of perfect cubes. We saw them in the last lesson and homework set, but we're going to review them right now. Exercise number 4. Prove the following identities using the area models. Letter A, x cubed plus a cubed is x plus a times x squared minus ax plus a squared. In other words, if I've got a perfect cube plus a perfect cube, I will always be able to factor it as x plus a times x squared minus ax plus a squared. Now, how do we prove this? Well, we actually prove it in more of the forward direction than the backward direction. In other words, we're going to prove that this product will always end up being equal to this. And let's do that together for letter A, and then we'll talk about the difference of perfect cubes in letter B. So, how do we prove this? Well, we're going to simply show that when we multiply these two together, we get that. It's, to me, easy to do this with an area model, right? We do this with a 2x3 rectangle. We've got x times x squared, which is x cubed. We've got x times negative ax, which would be negative ax squared. We've got x times a squared, which would be positive a squared x. We've got positive a times x squared, which is positive ax squared. Positive a times negative ax, which would be negative a squared x. And then we've got positive a times positive a squared, which would be positive a cubed. I just change color really quickly, all right? Because what we can now see is along the diagonals, here and here, we have what are called additive opposites, meaning that I've got positive ax squared and negative ax squared, negative a squared x and positive a squared x. So these two literally cancel out, these two cancel out, and what we're left with is simply x cubed plus a cubed. And we'll talk about these patterns a little bit, and obviously we'll also see how we can use them to factor the sum of perfect cubes. But let's talk about the difference of perfect cubes in letter B. Here we're trying to prove that x cubed minus a cubed is always x minus a times x squared plus ax plus a squared. And side note, look at how similar these patterns are, right? X cubed minus a cubed is x minus a, and then this trinomial and this trinomial are basically identical, with the difference being this is plus ax, that's hard to say that, and this one is minus ax. So what I'd like you to do is pause the video now, try to work through this area model to show that this product will always be x cubed minus a cubed. Take a moment to do that. I'm getting a little tongue-tied today. Here we go. X times x squared is x cubed. X times ax is going to be ax squared. X times a squared will be a squared x. Negative a times x squared will be negative ax squared. And let's see if we can make that look like a negative. Negative a times positive ax will be negative a squared x. And finally, negative a times a squared will be negative a cubed. Just like before, right? Along our diagonals, we've got additive opposites. That negative ax squared and positive ax squared cancel. That negative a squared x and that positive a squared x cancel. And what we are left with is just x cubed minus a cubed. Amazing, amazing. So how do we actually use these to factor? Well, let's take a look. First, let's just take a look at the sum and difference of perfect cubes formulas really quick to understand some structure. And we can just stay where we are right now. We've got x cubed plus a cubed. Notice the linear factor that comes out, right, will have exactly the same sign as here. So when we have the sum of perfect cubes, we then start off with x plus a. What we have in here, right, is an x squared and an a squared, both of which are positive, and then this kind of mixed term, a times x, but it ends up being negative, okay? We have exactly the same thing going on here. X cubed minus a cubed is x minus a, so that sign is exactly the same, right? But then inside of here, we have exactly the same trinomial that we did over here. We've got an x squared, we've got a plus a squared, but this is now a plus a times x. All right, now, whether your teacher forces you to memorize these two patterns or whether your teacher gives you those two patterns, I can't tell you because I don't know. You know, whether or not your state on its state exam gives you these two patterns or not, I don't know, right? And they can be a little bit challenging to sort of think about. But let's see how we can use them in exercise number 5. Use the patterns above to factor each of the following. Note the quadratic that remains cannot be factored. It is prime under the set of integers. All right, so really, really critical. This trinomial and this trinomial, which are both quadratics, right, x squared and x squared, they are prime. They cannot be factored unless you bring imaginary numbers in, which we're not going to in terms of the set of integers. So let's see how we factor in letter A. Here we have x cubed plus 125. Now, this is only going to work if 125 is a perfect cube, and it is. 125 is 5 cubed. Of course, if you have any question about that, whether or not a particular number is a perfect cube, you can always come out, take your calculator, put in the number, raise it to the 1/3, and see what its cubed root is. So the cubed root of 125 is 5. So if you have any doubt about whether or not that number is a perfect cube, then just take your calculator out and see what its cubed root is, and if it's a nice integer, you're good to go. All right, so let's go back in here and let's take a look. So we're going to think about x cubed plus 25 as being x cubed plus 5 cubed. And that means we're going to use the sum of perfect cubes formula. Now, what does that say? Well, it says that this will all factor into x plus 5 times x squared minus 5x plus 5 squared. All right, and again, let's just take a look at this, right? X cubed plus a cubed, x cubed plus 5 cubed, is going to be x plus a, x plus 5, times x squared minus a times x, a in this case is 5, so minus 5 times x, plus a squared, right, and that's 5 squared. The only thing that we want to do to finish this is write down x plus 5 times x squared minus 5x plus 25. And again, just to emphasize, right, that quadratic, x squared minus 5x plus 25 is prime. You cannot factor it unless you bring in imaginary numbers, and we're not going to do that here. All right. So let's take a look at letter B. Here we have n cubed minus 1. All right, the fact that it is an n cubed automatically makes us think, oh, maybe we've got the difference of perfect cubes. And of course, 1 is a perfect cube. It can be thought of as n cubed minus 1 cubed. It might be the most basic of them all right? So in this case, right, our x is n, and our a is equal to 1. Pause the video now and see if you can use this pattern to then factor n cubed minus 1 cubed. All right, here we go. Well, that pattern says that we should have n minus a times n squared plus 1 times n, right? A times x plus 1 squared. That ends up being n minus 1 times n squared plus n plus 1. There we go. Okay. Now, one thing I don't want you to forget is that when we factor something, we're always finding something that is equivalent to what we began with. So if you ever had a question whether or not you had done it right, one thing that you could do is take your calculator out, put this expression in, let's say as a function, maybe x instead of n, put this in as function 2, and see if they graph on top of each other. Or pull up a table of values and make sure the table of values is the same. All right, let's keep going. Now, we can certainly get into more complicated ones. Let's take a look at letter C. Here we have 8c cubed plus 243. That almost doesn't seem to be right, given that, here we have like just a variable squared plus some number squared maybe, right? So how do we want to think about 8c cubed plus 343? Well, thankfully, 8 is a perfect cube, right? So that can be thought of as 2c quantity cubed. And now you might, again, look at 343 and say, well, is that a perfect cube? Well, let me look, right? So 343 raised to the 1/3 is 7. So in other words, 343 is 7 cubed. All right, so I can come back in here, whoops, view full screen, and I can think about this as 2c cubed plus 7 cubed. All right, so now I'm going to be using this pattern. What do I do? Well, for x, we use 2c, and for a, we use 7. So that's going to be 2c plus 7. Now, remember, this is x squared, so that's going to be 2c squared minus 7 times 2c plus 7 squared. Now we've got some cleanup to do, and we'll get there in just a moment, but do you see what I've done, right? Everywhere there's an x, I've replaced it with 2c, and everywhere there's an a, I've replaced it with 7. That's probably the easier one. Now there's nothing I can really do with the 2c plus 7. That I'm just going to leave as 2c plus 7. And then this is going to become 4c squared minus 14c plus 49. All right, and that's it. Now, of course, what I'm going to do is I'm going to have you pause the video, and I'm going to have you try the most challenging one on your own. 27x cubed minus 64y cubed. Try to first frame it as some quantity cubed minus some other quantity cubed. Pause the video now and see what you can do. Well, thankfully, 27 is a perfect cube, right? It's 3 cubed. And 64 is a perfect cube. It's 4 cubed. So the first thing I'm going to want to do in letter D is I'm going to want to think about this as 3x cubed minus 4y cubed. I can now use this pattern, and everywhere I see an x, I'm going to have a 3x. And everywhere I see an a, I'm going to have a 4y. Okay, so this is going to get a little complicated here. So all of this is going to be 3x minus 4y times 3x squared plus, the squared should be outside of that parentheses, 3x squared plus 3x times 4y plus 4y squared. All right, so again, x and a don't have to be variables and numbers. They can be terms themselves. So I've got 3x quantity cubed minus 4y quantity cubed. So that's 3x minus 4y times 3x quantity squared plus 3x times 4y, that's my a times x, plus a squared, that's going to be 4y squared. Let's clean this up a bit. All right, and this is going to end up equaling, let me try to bring this down a little bit, 3x minus 4y times 9x squared plus 12xy plus 16y squared. Let me bring that down some so that you can see it a bit better. All right. And that's it. And that is definitely probably about as complicated as those things can get. Okay, let's do one last problem. Exercise number 6. Factor the following polynomial completely over the set of integers. All right, pause the video now and see what you can do on this. And again, it's got 4 terms, so that should immediately make you think, perhaps I should start by using factoring by grouping. All right, let's do it. So the first thing I'm going to do is I'm going to group these 2 terms and these 2 terms. And in the first 2 terms, I can factor out an x cubed, which will leave me with an x squared minus 4. In the second 2 terms, the best I can do is factor out an 8, which will also leave me with an x squared minus 4. That means I can then factor an x squared minus 4 out of both of those and be left with x squared minus 4 times x cubed plus 8. Now, before we kind of move on, let's just pause for a moment. Right? Anytime that we factor by grouping, very often after we factored by grouping, there's more factoring left to be done. And in fact, there's definitely more factoring left to be done here because x squared minus 4 can be factored as x minus 2 times x plus 2. And x cubed plus 8, right? X cubed plus 8 is the same as x cubed plus 2 cubed. So that now can be factored using the sum of perfect cubes, right? And remember, the sum of perfect cubes, x cubed plus a cubed is x plus a times x squared minus ax plus a squared. And that pattern's up top, but I wanted to write it down so we just sort of had it there. So now x cubed plus 8 can be factored as x plus 2 times x squared minus 2x plus 2 squared. And I'll just clean that up a little bit. And I will get something that looks like this. Wow. And that is some serious factoring. Factoring by grouping, factoring the difference of perfect squares, and factoring the sum of perfect cubes. All right, let's wrap this up. So in today's lesson, we actually reviewed many of the factoring techniques that we've seen previously in the course, right? We saw GCF factoring, we saw the difference of perfect squared factoring, we saw trinomial factoring, only a little bit, but we did see it, right? And most importantly, we introduced 2 new factoring patterns, the sum and the difference of perfect cubes. And they are definitely by far the most complicated of them all. If you have to memorize them, you definitely have to probably sit there and write them down 10 times just to kind of have them down. I certainly had to when I first learned them because they can be a bit challenging, no doubt about it. And perhaps, because of that, you'll have sort of that formulaic structure set out in front of you anytime you have to factor the sum or difference of perfect cubes. And in that case, all you'll really have to do is recognize that it is one of the 2 and then use that pattern to sort of fill in the blanks, if you will. All right, but it can definitely be challenging. In future lessons, what we're going to be doing is using factoring to reveal important properties about polynomials, the most important of which we got at today, which are the zeros of polynomials. For now, I just want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.